Hi, I'm Ben Martins. I'm one of the application specialists here at Pico Technology in the UK, and today we are going to be taking a look at one of our case studies. All of our case studies are on the website, www.picoauto.com, and obviously head to the relative sections to find the case studies. Now, this one, this was actually a two-part case study, which we've crammed into 20 slides, so keep up. No. All the information is on the website, like I said. It is a long one. It was one of the first hydraulic case studies that I got involved with, and a massive shout out here to Roy Sturgis, because his patience was, he had so much patience for a very green new person who'd not long started at Pico and just dipping his toes back into the hydraulic world after having not been doing anything with that for about 10 years. So here we go. So we have a Manitou MRT 2540 Plus with a winch attachment. Now this fault, the customer's issue, was the winch is slow. It's slow in both directions when compared to another machine. Now I'll say about the company that owns these Manitous, they had a number of them, which actually was very useful for us, because as we all know, known good data is vitally important in order to understand where your diagnostic path needs to go next. So, as always, our diagnostic process and method, speak to the customer, verify the fault, capture the evidence, build the picture, and then obviously confirm with the rectification. As we've sort of seen with other case studies in the off-highway and agricultural world, getting that confirmation or the rectification capture isn't always possible, and that is purely because they don't want that vehicle being down in any sort of downtime for any longer than necessary. So once you've fixed it, off it goes. Yeah, you might say to them, let me know in a couple of weeks and I'll come back and take another capture. You never get that call. So sometimes getting that rectification capture isn't always possible, but we should try to as much as we can. So the customer interview, the problem with this one, obviously the winch and it's just getting slower over time. Obviously the more weight on, or the heavier the lifting it's trying to do, the slower it is. So the machine is still operational though. So let's just say that. So it's only the winch system that they are complaining of. The rest of the machine still seems to be working okay. Now, we had a number of visits with, or they'd already had a number of visits for some other workshops and technicians. They'd given some analysis, but there was no evidence for it. So what the plan was for us was we were going to do, one, a little bit of learning, especially for my purpose as well, but also to show how Pico in this situation can help gather the evidence and justify the repair. So as always, our action plan, the first things we want to do, we want to get as much information about the vehicle, the wiring diagrams, component location. In this situation, a hydraulic schematic was absolutely vital. Hydraulic schematics, if you've ever seen one, they are complicated, of course they are. They like wiring diagrams. Once you get your head round and you can start breaking down different sections though, it starts to get easier, all right? We obviously want to collect our evidence. We want to do comparative testing. As I said, this particular company that owned this machine, they have a number of other ones that are all the same, which gives us a real good opportunity to get our known good data. Visual inspection, absolutely vital. More so in any case study, to be fair, your visual inspection is important, but even more so in hydraulics. If we are chasing a possible hydraulic fault, we want to make sure that there's no obvious leaks. We want to make sure that all the hoses are all correct and there's no issues with those. The last thing we want is a hydraulic injury at any particular point. As we go through this case study, we are using and we are measuring hydraulic systems. What I will say is that if you do not have any hydraulic training, please do not attempt to make any of these captures. It's a bit like high voltage. You wouldn't go and start disconnecting orange cables if you hadn't had the training, or at least I hope you wouldn't. Please don't go and start disconnecting hydraulic hoses if you aren't fully aware of how that machine works. There is a lot of areas where you can get it wrong and you can hurt yourself very easily. Okay. So the verification. It's a slow winch, okay? So how are we going to prove that the winch is slow? How can we capture the evidence? It's not always easy just to eyeball it, yeah? So in this situation, we used our optical sensor, and we had our optical sensor pointing at the rotating drum on the winch. And then from there, every time the drum rotates, we get a pulse. Now, within the Picoscope 7 software, we can then convert that pulse to an RPM because we're capturing against time. Maths channels can also be used, and they can also be used to then highlight what the actual RPM is and how it changes again over time. Now, in this capture here, we have also got the engine speed. Now, engine speed in this situation was captured from the injector. Now, our good colleague out in North America, Justin Morgan, he's actually done an article on how to capture and graph engine speed from injector signals, and there's the math channel that is within that article. Please go and check it out. It's a great way to get engine speed if you can't get easy access to, say, the crankshaft sensor. Now, in this situation, we have our winch speed as about 18.40 RPM. Yeah, about 18 RPM. Why have I included the engine speed here? Now, on this machine, the hydraulic system that controls the winch and obviously generates the flow is directly driven off the back of the engine. Therefore, engine speed is going to play a big part in flow rate. Now, remember, flow makes it go. Yeah, so we are dealing with a speed issue, so it makes sense that we are looking at a possible flow problem. Having the engine speed there means we can also now say that that is also the hydraulic pump speed. Now, this becomes more useful when we're actually doing comparative testing, because it might be that our winch speed at a higher engine speed would have been different, or if worse, it was actually lower. So it's important to have both. Getting onto the known good machine then, as I said, we have the luxury of a known good vehicle literally next to us. So obtaining that information was going to be vital. Now again, if we look back into this waveform, we have our, I'm sure if I can zoom in slightly, we won't worry, you can see that. Again, all these case studies are on the website, you can go in and have a look. Now we have our crankshaft speed on this. Again, it's probably just easier to get to. That's giving us our engine speed, and we obviously have the same setup where we have the optical sensor pointing at the drum on the winch, and we did it in the same way. So in both situations, I think they were going up. So the winch was being rotated up, okay? Using the maths channels, we can actually see that we have an RPM of 28. So it's nearly 10 RPM faster than our known, or than our faulty machine. So we can say now that actually there is a difference. Yeah, we are verifying the problem. We've captured the data, that then proves it, okay? What next? Okay, as we've sort of mentioned, because it's a speed-related issue, the most likely cause of this is going to be a flow problem. So we want to make sure that the flow rate we've got going on is correct. Yeah. So the one way we're going to be able to capture flow is using the Pico flow meters. They give us the ability to be able to capture flow, pressure, hydraulic oil temperature, and we've got a spare channel if we're using a 4-channel scope. So therefore we'd put, say, engine speed. As I said before, engine and hydraulic pump are connected directly, so we have a one-to-one output. So whatever our engine speed is means it's also our hydraulic pump speed. Again, with hydraulics, if you're going to put in a flow meter, you've got to be very, very aware of contamination. Yeah, the last thing we want to do is introduce dirt, water, any sort of contaminant into the hydraulic system. That's actually going to make our life harder. We don't want to make any more problems than what we've already got. So please take care. Avoid as much as possible. You know, there are situations that you just can't avoid, but as long as you're just trying to mitigate that as much as possible, that's the best you can do. Now the winch on this telehandler was part of the accessory circuit, so actually it was very straightforward to disconnect. They were on quick couplers. Again, an interesting point. Are the quick couplers okay? Yeah, again, we're dealing with a flow rate issue. In this situation, everything was good, okay? So, connection made, we then make our measurement. So, again, using maths channels, we can then plot our engine speed. We have our hydraulic pressure on channel B. the hydraulic flow on channel C, and the oil temperature on channel D. Now I've added in some measurements underneath there as well, so we can start again to make it easier to compare when we want to offer it up to the sister machine. So in this situation, at around about 1400, 1500 RPM, we have a hydraulic pressure of 181 bar. So how have we managed that? On the 300 and 600 litre per minute flow meters, there is a loading valve. When you turn the loading valve, you are simulating a load on that hydraulic system. So if I'm adding weight to that winch, I'm putting a load on that motor and therefore driving up the pressure. Yeah. So the whole basic principles of fluid power is that we want to maintain a flow rate for a given curve of pressure. Yeah, so we should always have adequate flow regardless of what the pressure is. So by loading up the flow meter, I'm starting to restrict the path that the oil has to flow through. But what we're looking for is that our flow rate should maintain, it should be steady. Yeah. Once we get up to a certain pressure, in this situation, the maximum pressure we could get was 180 bar with a flow rate of 9 litres a minute. Oil temperature, again important for the comparative to compare to make sure that they're both operating at the same temperatures. But those are the two key parts, 180 bar, 9 litres a minute. To me, 9 litres a minute seems a bit slow. So how can we prove that? Do the same measurement on the sister machine. So as we zoom in and look around that, well actually we'll just go back slightly because some of the figures that we obtained from this machine when loading up the winch or the accessory line was the maximum pressure we got was 220 bar. That was kind of, when I say maximum pressure, that was as far as we wanted to go before we start affecting the relief valve, okay? The flow rate, however, was still above 20 litres a minute. Yeah, considerably more than our 9 litres per minute on our faulty machine. Now obviously at 220 doesn't quite compare to the 180 we could only get out of the faulty machine. So we moved back through the waveform and we found the area where we had 180 bar, and in this situation we had 37 litres per minute. A massive difference compared to the faulty machine. Yeah. We are now starting to say that actually it is a flow related issue. It has to be, it's to do with speed. We've verified the fault and now we're actually getting to the point where we're diagnosing what the problem is. Yeah, we are now seeing that we have an inadequate flow rate at that pressure in order to maintain that drum speed on that winch. So where does obviously the flow come from? Well, it comes from the hydraulic pump. So that is the next thing to test. We want to make sure that that pump is capable of producing what it's designed to do. In this situation, we actually have to put a flow meter in line or from the outlet of the pump going into the valve body itself. So the valve body obviously is where all the controls and all the accessory lines go to. They are the bits that move the oil around to the relative system that you are demanding from as an operator. Now there are some dangers with this because the protection for the system is all done by the direct acting relief valve. Yeah, so that is like the safety valve. That's the bit that stops you over pressurizing the system. If I'm adding a flow meter in and then I'm going to simulate a load by applying a restriction to the flow, where's my protection? Yeah. Realistically, there isn't one. The relief valve is not going to do anything because we're on the wrong side of it. What I will say is that all the Pico flow meters do actually have a safety burst valve disc. When I say all of them, sorry, I should restate that. All the ones with the loading valve, so the 300 and the 600 litre per minute flow meters, they have a safety protection burst disc that sits in the back of the flow meter. If you go over 420 bar, which is what the default pressure disc that is fitted to the flow meters, it will automatically burst and then actually allow the flow. So it will bypass over the loading valve that we've wound in. All right, so there is some protection, but 420 bar might be too high for some circuits. So do please be careful. What is nice, obviously, about the fact that we are graphing this in real time, so we're in streaming, so anything over 200 milliseconds per division, we are seeing it in real time. So as we are loading the system, we can add a measurement, we can add like maximum value for the pressure, we can physically see how far it's getting. So we can protect ourselves a bit more by making sure we never go above what the working system pressure should be. Okay, so loading up the pump, we can then start to actually see what sort of flow rate we still have at the different pressure values. Now in this situation, the pump is still capable of producing 70 litres a minute at 250 bar, considerably different from what we had at the accessory line, where we only had 180 bar and 9 litres a minute. With that being said, then I think we can safely say the pump is more than capable of delivering more than what we are measuring at the winch. What I've done on this waveform as well, I've added in something called an XY graph. Now that allows us to plot two signals relative to each other. You'll often see people talk about hydraulic pump analysis, they'll talk about a PQ curve. Well, that is exactly what that is. It is pressure against flow. What that means is that actually we can watch that pressure flow curve in real time as we load the hydraulic flow meter. There is a whole other video on that in our off-highway playlist, which is also available on YouTube. So if you want to know more about that test, then please head over there and take a look. Now, we had to get a little bit of more input in some of this. Some of the controls, like I said, this was one of the very early tests that I was doing. And some of the schematics were a little bit hard to understand. So I did actually ask kindly the guys at the National Fluid Power Centre, really good guys over there, if you for a little bit of advice into this schematic, because there were bits of this that I was not sure how it should be working. So they asked, we sort of went down the different routes of where to go next. And one of them, they said to maybe focus on the load sense line. Now, load sense in this situation is actually used to help close the main stage of the direct acting relief valve. So in this situation, we have a dual stage or a two-stage direct acting relief valve. We have one that operates on the load sense and one that operates on the main circuit. So you'll see there that there are two values. There's 10 bar and 275. 10 bar is the main, well, I guess it's the main safety valve. Yeah, it's the one that will allow lots of flow out. Yeah. The 275 bar is actually our load sense circuit. Now load sense comes back, it's like a little pressure tap that comes off of the system, off of the main line, and actually comes back. Now if that pressure is always above 10 bar, it's going to hold that spring shut on the main stage of the direct acting relief valve. However, once load sense gets up to 275 bar, it will then open that stage, well then obviously then pressure drop will occur, and then obviously once the differential is above 10 bar, then the main stage will open as well. All right. So again, it's taken me a little while to get my head around all of that. I don't expect everybody out there to be hydraulic experts in schematic reading. However, there was that we needed to take into consideration, because remember we have a flow issue. Now, if my main stage of my direct acting relief valve is held open partially, or if my load sense setting is incorrect, that valve could be opening early. In that situation, I could be dropping all of my flow out the tank without it doing anything. Okay, good. We got through that bit. So, on to the next stage then. With that all set up, and actually the load sense circuit, it didn't really help us. It didn't really prove anything that we didn't already know. So the next stage was to look at, was then start thinking about, if we have a flow issue, there's no obvious signs of leakage, we know the pump's capable, where is the oil going? Because the oil must be going somewhere, because in theory, I should still have whatever volume of oil, you know, certainly more than 9 litres a minute, with a much higher pressure value as well. Yeah, so where the oil must be going somewhere. The only thing that we could think of from here was that there is an internal leakage within the valve body itself, within the valve block itself. So how could we prove that? Well, one technique was to actually disconnect the valve body or the valve block, and then add the end cap or the capping slice to the end and then create like a smaller valve block. Yeah, and then from there we could start to see if that was having an impact on the overall output of the accessory line especially. Now, time again is something that you don't have on your side, and especially when you're working on something that's, this was completely outdoors, there was no workshop, you've got light issues, we've got other problems with people trying to like pack up around you. It gets to 4 o'clock in the afternoon and the site are like, right, we're off, you need to finish now. So in this situation, we'd managed to rebuild the block up. We put our slice, so we've capped it off, we made a smaller valve body or a smaller valve block. We run the machine, but we only just captured pressure in this situation. But what we saw was that the pressure was massively increased. Yeah, we've got now 230 bar when we're operating and deadheading a section, yeah, of the accessory line. Massively different to our 180 bar that we initially obtained from the hydraulic winch when we loaded it. Yeah. This just helps prove that actually the flow of the oil isn't going to where we want it to go. So it kind of backs up the theory that we have an internal leakage within that valve body itself. Okay. Now, again, time being something that we don't have on our side, what we could have done was gone through each of them and actually worked out where the problem was. However, what we were finding was that actually even by disconnecting just some of them, we still had a problem. So the decision was made that a complete valve block was required. This was replaced, and then I'm happy to say it's all back and working. The customer is happy. Did we get the rectification? No. The machine was literally taken off of our hands and off to another job. Now, one of the big issues with this, in total, I've got sort of 6 folders from each day that we spent on this machine. In total, I think this entire job took around about a year. And that's no fault of anybody's. It's not the fact that we were being lazy and didn't have time to go and do it. It was just a number of different things that caused that sort of amount of time to be used. One of our biggest hurdles is that at the end of each day, that machine had to be back in a working condition so they could move it around the site. But this prevented a real problem when we were actually capturing the data, because realistically, if, for example, where we had to take the valve block out, that is most of your morning gone. You then got probably 2.5 precious hours, if that some days, of actual diagnosis time. So having your action plan is absolutely vital to know what you're going to do in order to maximize the amount of time you have to make those measurements. And obviously once we've done those measurements, we then had to put the machine back together again. So yeah, a number of different hurdles that we had to overcome in order to get that measurement and get the data to prove our theories we were on the right line. Again though, the beauty of having Pico is that you can collect the evidence. Like I said, I've got 6 folders with all the information. So if anybody said, what have you been doing all that time? You can say, here's all the data that we've collected. Here's the evidence. Also in this situation, what was absolutely vital was having that comparison machine to actually determine what was good and what was bad. More often than not, you'll have just the output values from the pump itself. You might not have what your accessory flow rate should be, or what the flow rate over back to tank should be from the valve block. All of that information is very, very, it's non-existent almost. So again, having a good machine, a good working machine with no complaints is really important to get that known good data. Okay, we made it. There was a lot of information in there. What I will say is that this case study was done over 2 parts. It's more like a novel than it is a case study. It's well worth a read. It goes through all of the pains that we went through, all of the things that we got wrong as well. Sometimes you learn by your mistakes, and that's not a bad thing. Again, a big thank you to Roy Sturgis there from RCT, because he really did have a lot of patience for this and in trying to understand the information that we could get out of this machine, but also for teaching me an awful lot of along the way. So I hope that helps. Thanks for watching, and as always, we will be back with you soon with another case study.